Hey everyone, it's question show time. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I will answer them here. As always, I record these shows live every Monday at 5 p.m. Pacific time. So if you want to get your questions answered live, handle follow-up questions, definitely join us on the live stream. Otherwise, you can post your questions on any video, anywhere you like, and I will grab a bunch of them up and answer them at the beginning of the show. All right, let's get into it. Sean Milner. Hey Fraser, if looking back in time to say 1 billion years after the Big Bang and you see a galaxy, for example, then would you be able to see the same galaxy, although aged, somewhere else in the universe, say 12 billion years after the Big Bang? I get that question a lot. And once people start to realize that when you're looking out in space, you're looking backwards in time. So when you're looking at things that are 1 billion light years away, you're seeing them as they looked 1 billion years ago. And when you're looking at things that are 12 billion light years away, you're seeing them as they looked 12 billion years ago. And so the question I think you're kind of asking is like, can you see the same thing at different moments in time? And the answer to that is mostly no. That when you see something, like say you see Andromeda, and when you go and you look in a telescope and you look at Andromeda, you're seeing it as it looked 2.5 million years ago, because it is 2.5 million light years away. But you're not seeing a version of Andromeda that is sooner or a version of Andromeda that is later. You're only seeing the one where the photons left the galaxy, traveled the distance, and have fallen into the telescope. Now, if you had built a telescope 1 billion years ago and pointed at Andromeda, then yes, you would see Andromeda as it looked 1 billion years ago. But then we didn't have telescopes 1 billion years ago. So for most of the time, whenever we see this thing, we're seeing it at the distance, we're seeing it at that time, we're seeing it the one time. Now, there's a couple of sort of interesting theoretical possibilities. One is that the universe is finite. It's not infinite, but it's actually some finite size. Now, most astronomers are fairly certain that the size of the universe, even if it is finite, is bigger than the observable universe. And so if the farthest we can see out to the cosmic microwave background radiation is 13.8 billion years, although that's now, 96 billion light years away. But if maybe the actual universe is, say, 1 trillion light years across, then we could never see things repeating. But if the universe was, say, only 1 billion light years across, and yet we would be seeing objects that time had taken them and the light had traveled for 13.8 billion years, then you would see things wrap. You know, when you're in an elevator and there's like a bunch of mirrors and you're like seeing multiple versions of yourself, it would be like that. So you would look one way and you'd see the galaxy, say 500 million light years away, and then you see it again 1 billion light years away, and then see it again 1.5 billion. And each time you would be seeing it, it would be looking a little younger because it's farther away. In the same way that when you're in that funhouse mirror, when you're in the elevator and you look at yourself, you're actually seeing versions of yourself that are farther away, and also the light has taken longer to reach you. And so you're seeing younger versions of yourself. You're looking backwards in time, out to the very limits of what that mirror will allow to reflect back and forth. So that's sort of the one way that you could do it. But most astronomers think that the finite universe is much larger than the observable universe, and so we don't see objects wrapping in the universe. The other place where this kind of comes up is when you get a situation called gravitational lensing, where you've got some galaxy cluster that is in the foreground, you've got some galaxy in the background. The foreground galaxy acts like a lens to make the light, to sort of focus the light from that more distant object. And if things line up perfectly, you can actually get multiple sort of versions of this background object being wrapped around this foreground object. And there's an example that astronomers actually found fairly recently. There was a supernova that went off in this distant galaxy, and astronomers saw it 3 times already around the foreground galaxy, and they've calculated that they'll see it a 4th time because the light has to take one path around this foreground lensing galaxy that is farther. And so it takes longer. And so we'll have to wait an extra 20 years to be able to see the fourth version of that supernova, even though it's the same one. And it's just that light, if light has to take a longer journey, then you may see it multiple times like echoes. So it's a pretty clever idea. Elementus. If we have a small star orbiting a large star, then could there be a planet in the L4, L5 points? All right, everyone's favorite topic, the Lagrange points. So of course, there are 5 Lagrange points in every 2-body interaction. So say the sun and the Earth, or the Earth and the moon, or the sun and Jupiter. You get these 5 stable points in space where the gravitational forces of the 2 objects balance out so that another object that is of essentially negligible mass can remain in the area, requiring very little propellant to stay in that same spot. The Lagrange 1, 2, and 3, the ones that are lined up between the 2 objects, they are gravitationally unstable. And so if you have an object sitting in, say, Lagrange 1, Lagrange 2, or Lagrange 3, it doesn't require very much propellant to stay in that location, but it will eventually drift away. But L4 and L5, these are the ones also where the Trojan asteroids are. They're ahead and behind the smaller object in its orbit, about 60 degrees. And so Jupiter's Trojan asteroids are actually the L4 and L5 points around Jupiter in its interactions with the sun. But the key word that I used there is that it has to be negligible mass compared to the other objects. And so you could have the Earth and the moon and a satellite, or you could have the Earth and the moon and a refrigerator, or the Earth and the moon and an astronaut. And the astronaut would remain at the L5 point, stably bound forever. And that's the key with the L4 and the L5, is that they're stable. They're gravitationally stable. If something falls into the L5 and stays there, then it won't fall away and drift away. But it has to be negligible. And so what negligible means just is dependent on the size of the objects. With Earth, we can have asteroids that are, say, a kilometer across remain in the L4 and the L5 Lagrange points, while Jupiter can have asteroids that are dozens of kilometers, even hundreds of kilometers across, remain in its L4. So the question is, if you had a binary star, could you end up with a planet? And I think the answer would be yes. That if you've got a star like the sun and then maybe a red dwarf star that's orbiting around it, the red dwarf is going to be much more massive than Jupiter. And so you would expect the masses of the objects to remain in its Lagrange points to be much more massive. For example, a small planet. And so you can imagine a situation, or maybe you just need to have like a supergiant star and then a sun-like star. But the part that's really weird, right, is then you would have the one star, you'd have the other star orbiting around it, and then you would have the planet not orbiting the star, but going ahead of it or behind it, actually in orbit around where the star is going. And then you'd sort of think about the dynamics of that, right? So the planet would be spinning, so it would have the day and night with the stars, but you would not have any orbit, or you would never orbit the star that you're closest to. You would always be ahead of it or behind it in orbit, which would be kind of weird. It's a clever idea. I like it. Shane Semler. Why have there not been any Io landers? It's the most volcanically active body in the solar system. It seems like an obvious potential mission target. We have never had a mission go directly to Io, which is Jupiter's closest volcanically active moon, the most volcanically active place in the entire solar system. And all the pictures that we got some pictures of Io from the Voyagers, pictures of Io from Galileo. I think we got some pictures when New Horizons made a flyby. I don't even think we've gotten any pictures from Juno, just Ganymede so far. Maybe it'll take some pictures. I don't think so. And that's a shame, because it is absolutely fascinating. It shows you what happens when you get these incredible tidal interactions with a rocky world like Io interacting with a planet like Jupiter. And I'm sure we could learn a tremendous amount about what those conditions would be like. Maybe it's kind of similar to what the Earth was like at the beginning of the solar system, what kinds of minerals are forming in Io. We really want to find out. NASA had proposed to send a mission to Io. They'd also proposed 2 missions to Venus, the Da Vinci and Veritas. And then they had also proposed a mission to Neptune to visit one of Neptune's moons, Triton. And they had these 4 missions, and they could only choose 2. And in the end, they picked the 2 Venus missions. And so the Io mission, the Io orbiter, and the Triton flyby were not picked up. And so it doesn't mean they'll never happen, but it means that they have been chosen for this next round of these small Discovery class missions. But I think Io is deeply underexplored. And as you look through the list of all the places that we need to really explore here in the solar system, Io is clearly one that's been overlooked and for too long. So my hope is that even though the mission wasn't chosen this time around, it'll come back around. I will do an interview with the principal investigator so we can talk about how cool a mission to Io would be. Balash Suhaja. Hey Fraser, what could a layman do to help push humanity towards colonizing the solar system? Learn in-demand astro skills, buy space services, invest in space startups? If you want, I guess what you're saying is that you want, how can we make humanity's exploration of the solar system happen faster? How can we get to that expanse future where we're living across the solar system, Belta Loda? Part of it is that there isn't going to be a lot of economic demand for a long time for this to happen. We're just really in the nascent stages of this whole process where sending anything out into space requires no longer the resources of a nation state. Now it just requires the resources of a very well-funded corporation and an entrepreneurial visionary. So hopefully the prices will come down to the point that more and more ideas can be tried out in space. But still, space is hard, brutal. Rockets explode, people die, hardware doesn't work the way you think it's going to work, and money is lost. And in fact, there's no better way to run out of money, to lose all your money, than to start, say, an asteroid mining company. They all go out of business. So it's kind of tricky. I think if you kind of go all the way back, like what got us to where we are? Lots of clever engineers working for NASA, working for SpaceX, working for Blue Origin, working for JAXA, the European Space Agency. So raising your children with an enthusiasm for space, for science, for going into the science, technology, engineering, mathematics fields, I think is like the best thing that we could do, is to return an appreciation for the fundamental role that science plays in our modern society. And it's so bizarre to me to see all these people that utterly depend on technology like smartphones and the internet and computers and YouTube and all this kind of stuff, and yet are dismissive about the scientific breakthroughs that it took to get us here. Like that's the foundation of our modern society and the progress that we are making. And so if that's shaky, then everything else that you try to layer on top of it is going to be not firm foundation-wise. So that's where I would probably put my energy, is science education, outreach, helping more people get funding, helping sort of deal with people who are like anti-science. That's probably where I would put my energy. Yeah. It's a tough one. Canon Lucas. Fraser, is it true that the Inspiration crew had problems with the toilet system during their flight? Inspiration 4, of course, was the 4 private astronauts that flew to space, launched by SpaceX a couple of days ago when I'm recording this, and they've landed safely, and it sounds like they had a great time. And I hadn't heard that they had any problems with the toilet, but the fact that it does have a toilet and the way the toilet was going to work was kind of interesting. The toilet is located very close up to the very top of the spacecraft of the Crew Dragon. And the people were theorizing that you could like sit on the toilet and look out the cupola, look out that window while you're going to the bathroom. But actually, it turns out that you actually need to close up that top chamber to be while you go to the bathroom, so it won't work. But I thought it was a pretty clever. That would be like the best bathroom in the universe. So, but I haven't heard any problems with the toilet. But if I hear of anything, I'll let you know. Forward synthesis. Hey Fraser, distance aside, how much harder would it be for a colony to be self-sufficient on the moon, Titan versus Mars? So we've got a colony on Titan, which is Saturn's largest moon. What have you got? You've got an atmosphere that's going to protect you from cosmic radiation. You've got an atmosphere that you don't need to have a spacesuit to walk around in. You just need a coat, a really good coat. But it's incredibly cold. Although it's also incredibly cold on Mars. There's very little sunlight on Titan, so you would have to have like a nuclear reactor. Solar panels just wouldn't work out by the orbit of Saturn. While with Mars, I mean, we've talked about what it's going to take to have a colony survive on Mars quite a bit. The gravity is low on Titan, just like it's low on Mars, so I think that would still be an issue. Distance aside, and the distance is the killer, but distance aside, I would say a colony on Titan would probably work better than a colony on Mars, except for the power problem. If you had a nuclear reactor, I think it would be easier to survive on Titan than it would be on Mars. Water's everywhere on Titan. Lots of the other gases and elements that are difficult to get on Mars are all around on Titan. So yeah, I'd go with Titan. Cryptoman 5000. Will Webb be able to image a planet from a close star system? Yes. James Webb will be able to take an image of a planet orbiting around another star. And the way it's going to do that is it's got on board a technology called a coronagraph, which blocks the light from the star and allows the light from the dimmer planet to be able to show up. But the onboard coronagraph that James Webb is going to be using is only really going to allow for fairly distant objects from the star, very close by objects, very bright planets, bigger planets. It would have to be just a few light years away from us with an Earth-sized world orbiting around for James Webb to be able to take a crack at analyzing and taking a picture of it. If this idea of a star shade could happen, then you would be able to have a second ability to block the light from the star, and that would push out the capability of James Webb to be able to image a much larger area, be able to get a much better shot at being able to image some planets directly. But it's also, I think, important to understand what it means to say imaging a planet directly. At the very best, you're still only going to get one pixel. Like, you're not going to get a picture of the planet. You're just going to get one pixel of light that is coming from the planet. And in that pixel of light, astronomers are going to be able to break up the light into its spectrum, be able to see the different kinds of chemicals that are in the atmosphere of that planet, and try to be able to determine if there's life there or what is happening. Is it a water world? Is there lots of water vapor in the air? Does it have a hydrogen-rich atmosphere? What's going on? So even in the very best situation, we're going to have sort of secondhand data about what's going on with those planets. It's still going to be the best data astronomers have ever had, but we're still decades away from really powerful telescopes that could actually take a picture of a planet and show you continents and oceans on that planet. That's still kind of in the realm of science fiction right now. Lenny Lung. Won't the universe just be all black holes at one point? It seems like a likely possibility, doesn't it? That any matter that gets too close to a black hole falls in, and so given enough time, every star, galaxy, planet, piece of gas, dust is going to make its way into a black hole, and then eventually you'll just have black holes of varying masses across the universe. Now, they all won't turn into one black hole because the expansion rate of the universe is accelerating, and so there are various black holes that will never be possible to meet. But actually, you won't get all the matter in the universe falling into black holes. You'll definitely get lots of it going into black holes, but there will still be lots of other degenerate matter. Like a star may die, explode as a supernova, turn into a neutron star, or expand as a red giant, turn into a white dwarf. So you'll have white dwarfs out there that just never happen to run into a black hole. You'll have neutron stars that never happen to run into a black hole. You'll have planets that were kicked out of their star system and just roaming around the universe, and they just never found their way into a black hole. So the far, far future is going to just be black holes and then stuff that didn't fall into black holes. But there won't be any stars. It'll just still be very dark. Nelson Fernandez. How far do you think a man-made object will ever reach? Like, we know that the Voyagers are on their way, leaving the solar system, and say in about 50,000 years, they'll reach the distance of Alpha Centauri. So that is 50,000 years to go about, let's say, 5 light years. So they're going about 1 light year every 10,000 years. and the voyages were designed to last about 1 billion years before they get worn away. So that should be far enough to take them all the way across the galaxy. So I think given billions of years, there will be human artifacts that will be able to get pretty much anywhere across the entire Milky Way. We won't be alive to see it. I mean, you got to be really, really patient, but I think that's perfectly reasonable. And then if you can build something that's even stronger, then you could theoretically pass the gulf between galaxies, the millions of light years in between galaxies. You just have to go a little faster. I mean, right now, the Voyagers aren't going super fast, but theoretically, we should eventually be able to send stuff 10% the speed of light. And then you can imagine over billions of years, they will go hundreds of millions of light years away, pretty much to all the galaxies that we can see in the night sky, all the close by galaxies. That's all perfectly reasonable. It's just like, if you're patient, then things can happen over long periods of time. It's just that we're not patient, and we're not going to survive for that long. But yeah, it's sort of an interesting thought that even as the sun is consuming the inner planets, that humanity has long died off, in theory, some of our artifacts will still be out there in space. They'll be cosmic ray blasted, melted blobs of metal, but we made them. Miguel Angel Romero. Hey Fraser, if Starship works as intended, do you think that we can expect a near future with missions to all the planets and its moons? So let's define this here. So if Starship works as intended, that the Super Heavy is able to launch multiple times a day, Starship is able to launch a couple of times a day. Each one is able to carry, say, 100 tons to orbit. It's fully reusable using ecologically sound, artisanal grown methane fuel. Then absolutely, we will run through the entire manifest of launches. All the Starlinks will be launched. All of the other constellations will be launched. And then people will be able to purchase flights to various destinations across the solar system at a fraction of the price. Like, when you can have a satellite that the launch costs are effectively free. Like right now, when NASA is planning a mission to, like, the Titan Dragonfly, yeah, they're looking at however many billion for the mission, and then as well an equivalent number of hundreds of millions to billions of dollars for the launch. So in theory, Starship will be able to bring those costs down to a couple of $1 million. Like, it's effectively free for NASA. And so that will free them up to send all kinds of spacecraft. And instead of building great big flagship missions, they could build much smaller. Maybe they could build a mission for $20 million, $30 million, and then build a bunch of them. Build an asteroid explorer class mission, and then build 20 of them, 50 of them. So imagine Starlinks, but science probes sent to all kinds of objects across the solar system. Yeah, I think that's super reasonable, that we could see proper close-up exploration, at least with orbiters, of every meaningful object in the solar system within 20 years, I think. Seems reasonable, if Starship works as we hope. Gwym. If metallic hydrogen were metastable, how big a deal would that be for aerospace? So metallic hydrogen is the stuff that's found at the center of Jupiter. After you take all of the immense gravity and pressure inside Jupiter to mash hydrogen down where the atoms are so close they start to behave like a metal. It is an incredibly dense fuel. And if we could generate metallic hydrogen in large quantities, or like any kind of quantity here on Earth, it would be a total game changer for space exploration, because the energy density is off the charts compared to anything else that we have. When you imagine those spaceships in the expanse where they've got some fusion drive and they just lift off and they fly off into space, that's the kind of spaceships that metallic hydrogen would enable. The challenge is being able to actually generate this stuff, being able to store the stuff. Like, we don't know if you can make, like, people have said they think they've made metallic hydrogen where they have like diamond vise, and inside that diamond vise they're able to generate enough pressure to mash the hydrogen down so that it can form this metallic form. But as you release the pressure from your vise, does it just bloat back up into regular old hydrogen? How do you keep it under that kind of pressure? Jupiter does it through the mass of Jupiter. So there's a ton of technical issues. But if we could solve it, then yes, it would utterly change the way rocket ships work. That you would have the equivalent fuel of a Saturn V rocket in a much smaller volume and weight. It would be incredible. Yes, please. Mark Carter. Can interferometer telescopes in space, depending on the distance between them, see bright objects at any distance? So we talked a little bit about interferometers a couple of episodes ago, and so I'll just go over it a little bit again. So the idea with interferometers is that you can take advantage of this really clever trick with light, that you can separate two telescopes apart, and as long as you have them aligned so that essentially the wave fronts of the light are arriving at exactly the same time, down to one wavelength of the light. So in the case of visible light, say it's whatever, 500, 700 nanometers. As long as you can keep the distance of your telescopes within nanometers of each other, then those two telescopes can act like a telescope that is the size of the distance in between them. It allows you to get the resolution. So in other words, you could see small objects, but it doesn't give you the ability to see dim objects. It doesn't give you the brightness. And so to have the brightness, you actually need to have the in-between telescope part. So theoretically, if the thing you were trying to look at was very bright, like a quasar or the event horizon of a black hole or a star, something that was giving off a lot of energy, then yeah, the bigger your telescope, the more you're able to make these tiny resolution measurements of anything that's very bright. But the list of those really bright things starts to run out after a while. And what we're really wanting to do is be able to see the things that are very faint. And so that's why, for example, like the Event Horizon Telescope was a collection of radio telescopes around the world that were imaging the supermassive black hole at the heart of M87. But the world's radio scientists are really excited about the creation of the square kilometer array. And in this case, they're going with all the telescopes in between part. They're building one full kilometers worth of surface area on their collecting region. So not just the telescopes are separated 1 kilometer apart, but you've got 8 kilometers worth of telescope. When you think about, say, Arecibo was a few hundred meters across. The FAST telescope is like 500 meters across. So you're looking at a square kilometer. It's going to be an enormous radio telescope. And that will allow you to see faint things like cosmic dawn, like the time when the first clouds of hydrogen gas were starting to form at the universe shortly after the Big Bang. You need a lot of collecting area. But an idea that I really like, and we talked about this one time in an episode, was that people have proposed building very crude interferometers. So instead of trying to align your telescopes perfectly so they can act like one telescope, if you just launch two telescopes that are the same size, it acts like the total surface area of those two telescopes. So in other words, if you have one telescope that's 10 square meters of space, and then you launch another one that gives you 10 square meters of space, then they act like 20 square meters of space total. And if you launch 100 of them, or 1,000 of them, and they just fly in a cluster, and they're not trying to align, you still get the equivalent. If you add up all of those separate telescopes, you get that equivalent as a telescope. And so there's been some great ideas about, like, instead of trying to be really careful about it, let's just launch a bunch of light buckets, have them fly in formation, not try to get the same wavefront, and you could, over time, as you just add more telescopes to the formation, create a bigger and bigger telescope. Next week, you add another 10 meters, 20 meters, 30 meters, 50 meters, 100 meters to your telescope. And so maybe bringing it back around to that first question, talking about Starship, like maybe that's what Starship does next, is they come across some kind of plan for building some sort of telescope platform that's cheap to produce, that works really well, but is not this sort of really expensive, folding, complicated machine. And then you just try to, over time, if Starship has some extra space, it just launches more of these telescopes into that formation, and that telescope just gets better and better and bigger over time. I like that idea a lot. And like I said, I've seen some studies that have considered that kind of an idea, and I think it's really strong. So hopefully someone will investigate it again. That wraps up this week's questions. Thank you, everyone, for asking them either in the YouTube comments or showing up to the live show and asking your comments directly. I have a lot of fun with this. I will see all of you next week. If you want a single comprehensive resource for space news, you want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all of my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, Chad Weber and Nancy Graziano.